Thank you, Peter, and thank everybody for coming. Our talk today is about Caloosahatchee. We have been monitoring oxygen in the river since 2007 with RECON. Our RECON system is, I'll talk about in a bit. This is basic. So, hypoxia is defined as insufficient dissolved oxygen levels or aquatic life. And we have a diagram here that shows basic process, excess nutrient loading, organic loading, feeding, production, and feeding, Benthic decomposition. And hypoxia occurs when decomposition exceeds the rate of production in water column or the rate of resupply of oxygen from the feed. Another thing that can affect hypoxia is stratification and dark water prevent light from reaching the bottom and reaching phytoplankton to spur oxygen production in water column. Stratification prevents water from surface from exchanging with water at the bottom and bringing oxygen to the lower layer. Then a global increase in hypoxia, as shown on the graph on the left, in the numbers and reports over the years. The map on the right that shows how widespread the problem is, and it's becoming more widespread as the population grows. Why hypoxia is bad is because it affects benthic organisms such as fish and fauna, invertebrate shrimp. The graph on the left shows that the level of oxygen that most species are affected by is over 2.28 milligrams per liter. So animals that are experiencing hypoxia, when you move somewhere else at levels below 5 milligrams per liter, if they're sensitive to that level, they move. So we have about 50% of the species that are affected at levels above what is considered hypoxic in many areas of the level of 2 milligrams. The reason hypoxia is bad in Florida, or worse in Florida, is because our temperatures are higher. The temperatures cause more respiration, greater demand for oxygen, so the 2 milligram per liter level is really insufficient to use as a standard for Florida system hypoxia. The graph on the right shows the effect of temperature on lethal response of a muscle permanent. And it just shows that the temperature is much lower than we have here. We're stressing organisms at a higher levels of temperature. Shrimp are one species that's important economically in Florida that avoids hypoxia. It avoids levels less than 2.5 milligrams per liter. It also avoids salinities less than 5 kg. So, with a lack of benthos for feeding, that's one reason the fisheries would be affected. The fish will swim elsewhere if the water is hypoxic, as long as they are able to swim. But other factors are affected by hypoxia, including improvement, species diversity. This map of the Chesapeake Bay shows green spots where biomass of the fishery trawls were highest, and you see where the water was hypoxic in the red. There are very few catches. So these effects on the ecosystem translated to lower fisheries yield, will affect tourism, the economy. In the Chesapeake Bay, they've been monitoring hypoxia for a number of years. shows how nutrient loading affects hypoxia. And they have a lot of nutrient loading from a large watershed, including the Susquehanna River, and also its point sources. So they developed a way to predict how bad hypoxia will be using this model. This graph shows the effect of stratification on hypoxia. This stratification is where freshwater flows over saltwater, and the water is not mixing very much, so oxygen doesn't get translated down into the lower level to replace what is being taken up by benthic respiration. The phytoplankton blooms and organic matter that are loaded into the system from surface water are sediment into the bottom where they take up oxygen. The other thing this diagram shows is that the light level that penetrates into the water column is reduced from having dark water. That reduces the oxygen production, net primary production of the system. And this relates to our system in Caloosahatchee. So I'll talk a little bit about the Caloosahatchee's hypoxia problem. This is a graph or a picture showing clams that were floating down the river in 2009. After and during the hypoxic event, the hypoxic event is shown on the bottom of the graph. That's oxygen at our Fort Myers RECON sensor. The temperature during this period where the clams were washing up near the Orange River were up to 35 centigrade, which is in the lethal temperature range. When you have high temperatures in association with low oxygen levels, that's deadly even for clams too. Even though clams are pretty adapted to hypoxic conditions and most ready to withstand. In the Caloosahatchee, we have a large watershed. This is shown by the area outlined in white north of Lake Okeechobee. That's our standard watershed. The outline at the bottom is in red is our previous watershed, and the green outline west of that. So this expanded watershed is 4 times the original watershed size. The graph on the left, I compare this is comparing Chesapeake Bay's watershed to water ratio, water surface area ratio, showing that it's much larger than most systems. Caloosahatchee is about 4 times larger watershed area to surface area ratio than the Chesapeake Bay. This relates to an increased nutrient loading per meter square, shown in the graph on the bottom. The graph on the bottom of Caloosahatchee is the highest number on the right there. That excludes some other systems that have very fast turnover times. And our Caloosahatchee turnover time is also faster than Chesapeake Bay, which is lower on that line. So this graph on the left shows the flows in the last 10 years and shows that in some years we have hurricanes have very high flows. In 2013 we had a wet year and had very high flows compared to other years. The graph on the right shows the percentage of the flows that come from Caloosahatchee at S79 that come from the lake. The lake percentage is in blue at the bottom. So it's about 50% of the flows from Caloosahatchee come from the lake during high flow periods. This doesn't translate exactly to the nutrient loading, but that's the general during the high flows. During the low flows, the ratio is much more slanted towards the Caloosahatchee watershed. In the case of 2013, which is the flow, or these are nutrient loads on the left, phosphorus on the top, nitrogen on the bottom. 2013, we had not quite the level of nutrient loading that would meet the TMB up. That's 4,080 metric tons per year. So, but it was a very high flow year, very high loading year. So it makes it look like that level was, that R was set up too high. It's much higher than average of 1996 to 1984 nutrient loads. The pink graph on the right shows the percentage of phosphorus loading that comes from upstream of F79. The others are tributaries like Trout Creek and Orange River that are west of F79. So most of the loading comes from upstream of F79. The particulate nutrient loading I'm showing in the picture here from 2013, this is Mote that just ripped out of our RECON unit when we were servicing it. That's particulate loading from the watershed that settles out where in any quiet area, in any low turbulence area. And this includes refuge impoundments, and this particular settle out in the impoundment settings, nutrient for the oxygen demand in the impoundments and increased hypoxia there. We have sign factor winds in the river almost every year when the locks are closed at S79. This produces organic matter that settles out and also increases oxygen demand and affects Edmunds and SAD by shape. And in the rest of the estuary, near Fort Myers, we have blooms of Diamondophyllus during the dry season. These produce organic matter that settle at the bottom, take up oxygen, and cause oxygen demand problems in the spring and summer as water warms up. And downstream, too, we have nutrient loading problems, causing excess algae production, which contributes to oxygen demand. This can possibly contribute to hypoxia offshore, but we don't have a monitoring system right now. When we did have seagrass, K-grass in the river, that K-grass could produce oxygen, which would reduce the demand reduce the oxygen demand by increasing oxygen concentration in the water. The graph on the photo on the right just shows that we don't have as much biomass anymore, and we don't have that production, so we're kind of behind in oxygen production. Benthic production should be one of the major producers of oxygen in the estuary. Reduce oxygen levels and reduce salinity levels in the wet season to produce effects on the benthic fauna. This graph on the Green Lab shows that we have lower benthic invertebrate numbers and diversity than the average for the system, or the trout harbor system. So the purpose of this talk is to increase awareness of hypoxia, and we're trying to use the data we collect to quantify the effects of nutrient loading on hypoxia or TMDL refinements. This is a photo of just what one of the things that happens when you have hypoxia is the only thing that can grow is contour graph went down to 0.17 milligrams per liter upstream of beautiful eye, and it was most likely Hypoxia east of that, as that's where the power plant and the warm water was. The graph on the right shows the temperature gradient increasing up towards the power plant. The oxygen level probably became apparent after we looked at the RECON data from that year and for real-time data. And it was occurring as the flows were increasing to 1,500 CFS. So we've been monitoring hypoxia each year at RECONs and doing transects across the distance between Fort Myers and Beautiful Island. And this graph is between 2010 and 2012. We have levels of hypoxia down to 0.2 milligrams per liter every year in that stretch. In 2013, we had a mild hypoxia episode, but it was quite extensive. It extended from Fort Myers. This is where the orange extends down to where the western extent was, but it extended past the belt of 25 miles. This surface layer was also hypoxic, but it was less hypoxic than that. And at Fort Myers RECON, I've just shown here that we have different levels of hypoxia every year, but our worst year so far was in 2008, where we had hypoxic index of 3.7. Compared to other systems, it doesn't look bad, but other systems are often affected by organic matter load from like mangrove leaves. We also have 5 BOD loads that contribute to hypoxia. This is BOD's oxygen demand of the water itself as it comes in through S79. And these nutrient loads contribute to increased concentrations above the limiting level for phytoplankton algal growth. This is changing every year based on the water flows. When we have high flow year, levels of nutrient around Sanibel near the Peak Harbor National Wildlife Refuge get to be too high to keep phytoplankton growth under control. So we have hypoxia events here. Our RECON systems are helping to detect those. We have a need for nutrient load increases to reduce the severity of hypoxia. The system production is depressed, which is affecting most of the animals in the system. And we help have a model that would be able to determine which loads reduce hypoxia. Stop me home. I'd like anybody to come. RECON centers were paid for partly by these groups here, but also by volunteers and our members.
That was a big deal. We could all get our volunteer citizens to support our science as well as the CCF has got in their hopes to support this community. It would be a better world.
I have a question. Is the cyanobacteria toxic? I'm not sure. Yeah, is cyanobacteria
So the question was, is cyanobacteria toxic? And the answer was yes, some species